All right, welcome back. Stoked to introduce Cody. He's going to be talking about picking the Mac chain on macOS. So not only are your AirPods not safe, apparently neither is your keychain. So Cody, take it away. Round of applause.
Thank you, everybody. Welcome back from break. So like Patrick mentioned, I'm going to be talking about lockpicking the macOS keychain. Don't worry, Apple, I'm not dropping O days or anything, so don't have to worry about that. So who am I? I'm Cody Thomas. If you do the whole Twitter game, I'm at It's a Feature. That's why I love the previous presentation that said it's not a bug, it's a feature. I live by that motto. I created and spent a lot of my time working on a C2 framework called Mythic, formerly Appfel. Been mentioned a couple times here at the conference, tends to do a lot of red teaming on macOS. I'm also one of our instructors for a Mac Tradecraft class. And I have a kind of love-hate relationship with JavaScript for automation. I hate how much I love it because it gives me so much pain, but it is so useful. So today, we're going to be talking about a couple of things. What is the macOS keychain at kind of a high level? Why am I even targeting it in the first place? What are keychain items? How can we access them? And then 3 kind of case studies of some fun things that you can find or do with the keychain. So what is the macOS keychain? Whether or not you intend to, you are using the keychain pretty much every day. Even if you aren't explicitly storing things in the keychain, applications are storing things in there on your behalf. So the whole point here is that to provide some way for applications and users to store sensitive data on their computer for easy access without having to do all that management yourself. Pretty easy, pretty nice, works really great. So we can see here, as a user, you can store things like passwords, cryptographic keys, so if you're a developer and you're creating new private keys or stuff like that to use when you go sign applications or anything like that, saved right here in the keychain. Any certs or identities saved in there. If you're doing any sort of secure notes, all this kind of goes in the keychain. Now, one thing that's important to note to kind of level set as we start talking about this, there are actually 2 different kinds of keychains that exist on macOS. This is a relatively newish feature, as we've seen already that macOS and iOS are kind of coming together in how they bridge things. So there is a file-based keychain that exists on disk. We'll talk about that in a second. That's really what the point of this talk is going to be on, those file-based keychains. There's also a data protection keychain that exists on macOS that is backed by a database, not just a flat file on disk. And this is for your iOS, iCloud, iSyncing, like all this sort of stuff is backed up in here with even more protections. So that is better. If you can use that by all means. But as legacy, most things on macOS that you're doing are going to be using these file-based keychains. So for your standard user, there are 2 by default. Your user will have one in your home folder, library keychains, login.keychain-db, and then the system is using one in library keychains, system.keychain. So the data that gets stored in these is a little bit different based on if you're looking at the user's login keychain or the system keychain. So your user login keychain is going to have your internet passwords, the ones that like in Safari you go through and say, save this thing. If you're doing user-created certificates, if you're connecting up to Wi-Fi, stuff like that. Your system one is going to have, as you might expect, more of your system-based secrets. So system private keys, root certificates, all this sort of stuff is going to kind of be swept up in there for management. Now, there is a way by default that you can go ahead and interact with the keychain on macOS. This is the keychain access.app. Looks like this. Pretty straightforward. You can see here your login keychain, system keychain, all the different things that are going to be in here. You can interact with them, see information about them. And if you authenticate, you can then see the secret that's kind of stored in there. So why are we even talking about the macOS keychain in the first place? I come from an offensive background, so I'm looking at this as from like a red teamer pen testing perspective. So traditionally, what we do from the red team side of the house is because there aren't really protections around these flat file keychains, we download them. First thing you do, you get on engagement, you're that user, yoink, download that keychain offline. The sensitive data in that keychain is still encrypted, but if I can get the user's plain text password later, offline on my own VM, I can then decrypt it, get all your secrets, and go about doing all these other things. So the downside there is that 1, you have some random process that's going to be reading the keychain and downloading it offline. And 2, you need the user's plain text password to be able to decrypt it. Now, there are a lot of awesome protections on macOS that make it kind of hard to get the user's plaintext password. Now, we've already seen and discussed a whole bunch that people are used to typing in passwords into prompts on macOS, so it's not uncommon to pop a dialog box to the user, ask for their password to do an update, install software, check virus scan, like all this sort of stuff. And more often than not, users will type that in, but I don't want to have to deal with that. So my goal in trying to look at the keychain is seeing if there's a way I can go through without downloading the keychain from the computer, so I don't want to touch it at all. Can I go through and pull out data, sensitive secrets from that keychain without prompting the user? Specifically, as we're going through and doing this analysis, even if I'm wrong, I don't want to cause a pop-up to the user. There is a technically deprecated API that's super handy for this. The set keychain, set user interaction allowed API. I just hit that to false. And so even if I'm wrong and I try and decrypt your plain text data, I won't cause a pop-up. I just get a silent error. So that's pretty nice. I also don't want to have to know your plain text password. If I already had your plain text password, then I could just decrypt all the things in the keychain anyway. The point is that I don't want to have all these requirements. I want to go ahead and find misconfigurations, and I want to avoid as many detections as possible, kind of ride what is valid and get things that way. I don't want to have to do command line stuff. I don't want to have to touch files. Let me just use APIs and do this. So naturally, offensively, I try and go through, are there GitHub projects, are there things that I can use and do this? There's not a whole lot of tooling out there, so I created my own. This is an open source tool that I just published on GitHub maybe an hour ago. So feel free to go ahead and pull it down. It's called Locksmith. As you compile it, it'll generate a Mako and a dylib that you can use. There's also a complementary Locksmith Lite that's doing a lot of the same sort of stuff in JavaScript for automation. And we'll talk about why that is pretty useful here in a bit. So the next thing to talk about is, what are these keychain items in the first place? Why am I pulling stuff out? What does it look like? What information am I getting? In general, keychain items consist of two things: the encrypted secret thing that you're trying to save into the keychain, and then all the attributes and metadata surrounding it. So we can see an example here, just looking at an example keychain entry for Slack's safe storage, some metadata and attributes that are associated with it that's not encrypted, things like the account name, the label, creation date, what kind of entry is this? Is this a password? Is this a internet password? Is this a key, a certificate, identity? Like, what is this thing that we're looking at? The other big thing that's associated in all these attributes is access control lists. So every keychain entry has a thing that you're trying to store. So you're storing something in the password, ideally for use later on, right? You're saving a password that you can use it to then log in somewhere. You're saving a key so that you can use it to sign something, right? You're saving a certificate so that you can use it to validate another trust hierarchy. Like, they're being stored in there for some reason. So as part of this, we have to kind of lock down what applications can do with this data that's stored in here. And so all this is captured in these access control lists that have a set of operations, can use it to decrypt, encrypt, sign, derive keys, export. Like, what is it you're trying to do, and who can do it, okay? So offensively, there are a couple of these kind of operations that I'm interested in. Specifically, can I export it in clear text? Can I just see whatever it is that you tried to save? Can I export it wrapped? So this is a little bit different, but all this means is that when I export it, it has to be locked behind a password. So think like a private key that has a password associated with it. I can still get the data. I just have to set my own password. Okay, fine, I can deal with that. Also, authorization any. As you might expect, you can do anything. So that one's a pretty dangerous one, and we'll see that crop up a little bit. So in addition to this, like I mentioned, you have these set of operations, and you have a set of who can do it. So this is a list of trusted applications, and it can be one of three things. So you either have nil, a null, nothing here, which means everybody is trusted. Every application can do these operations. It is an empty list, which means that nobody is trusted. No application can get this data and do these things. Or it is a list with at least one application in it. Okay? So those are the three kind of scenarios that go in there. Now, as we go through and we start looking at keychain entries and looking at these access control lists, some of them are pretty straightforward, some of these operations. So, like I talked about, export clear, the authorization to sign, to encrypt, all this sort of stuff. There's two that were kind of opaque, not quite clear what they're doing. There's ACL authorization integrity, and this one down here, this ACL authorization partition ID. What stood out about it is that the description is this super weird long hex thing. So not a standard description for something that you might find. The other thing that seemed weird is if you can see down here at the very end, the last thing is 0A, so a new line. Something's fishy going on here. So I, naturally, go to Apple's documentation to try and figure out what's going on. The first thing I see is, sweet, all the keys, all these operations are broken out for me with short descriptions as to what they are. Fantastic. Except for the two that I'm interested in. So it's like, okay, no worries. Maybe there's just not a short description for it. I click into it. Okay. All right. I do believe that this is a key. Yes. What you can do with it, what it means, what is this weird hex blob? Fine. I will figure it out myself and go kind of dig into it. So if you take that whole hex blob and convert it into ASCII, it's actually, as you might expect on macOS, a plist, because everything is a plist. Inside of that, there is always only one key called partitions. And there are only a couple of things that go into this partition key. So it will either be team ID colon and then a team ID. It'll say Apple colon or Apple-tool colon, or it'll say CD hash colon and have a CD hash for a binary. So what this is actually doing is trying to identify the owner of this keychain entry. So it can be locked down specifically to a user ID, so like UID 0 or UID 501, or a certain group owns this keychain entry and thus has extra permissions and authorizations that they can do on it. If you don't set a specific user, then it defaults to kind of the application that created it in the first place. And so if, for example, Slack or Google Chrome or Microsoft Teams or some application stores this entry in the keychain, this partition ID will automatically get created with that team ID. If something Apple creates it, so think the Keychain Access app, if you create an entry in there, then the owner will be Apple colon. It'll be a very specific Apple signed application is the only thing that can access this. So this will come into play later. Now, if you go through and just look at that Keychain Access app and you create a new password, save something in there, you will get 5 ACLs by default. So one will say everybody can use this to encrypt things. Nobody can use this to export or decrypt. All applications can see the integrity check. Nobody can go through and change the ACLs, which is really nice. And the partition ID will be set to Apple colon. So the way that this is kind of broken out is that all applications can do non-dangerous things, and no application can do the like quote-unquote dangerous things. So like exporting your password in clear text, using it to decrypt sensitive data, all this sort of stuff. All right? Choice. I like it. If a normal application goes through to create a keychain entry, not using the Keychain Access app, it's just slightly different. So it'll just take the information from the application that tried to create it. So say Google Chrome, Slack, Zoom, what have you. They go through and create an entry into the keychain. It'll say all applications can encrypt. Only that specific application that saved it into the keychain in the first place can export the clear text, can decrypt, all that sort of stuff. And then the only other thing that changes is the partition ID. It gets set to team ID colon and then that corresponding team ID. Okay? Easy. If we look at this in the Keychain Access app, we can generally see this. On the left-hand side, this is one going through with an entry created by Keychain Access app itself. So nobody can go through and get this data without prompting. If a specific application created it, here we can see Slack is able to go through and pull out the data without prompting. Okay, now we have an idea of how this sort of stuff is set up, a kind of high-level overview of what these ACL entries are. So how do we go about accessing the keychain in the first place? Well, naturally, there is a built-in tool that you can use. So the security tool can do a lot of things on macOS. One of them is the dump keychain command. So if you do security dump keychain tac A, it'll dump out all of the metadata for all of the entries in the keychain. You're not getting any of the encrypted secret data, nothing that's stored in there and encrypted, but everything else. If you pass in the tag D, then for every entry that it processes, it'll try and decrypt it. You're using the security tool, so you won't match all those like team ID, partition ID hashes. So then you'll get all these pop-ups. You'll get a whole lot of pop-ups because, surprise, there are a lot of things stored in your keychain. You can use the find generic password subcommand to go through and just look for specific things. So you can say, I just want to look for passwords where the account is Slack. The tag G in this case says to try and decrypt, because naturally that's what you think when you see G. You can also go through and set the generic password partition list. So this is what we're looking at before that had the like team ID : or Apple : You can explicitly set that to anything that you want. Naturally, you will have to authenticate to be able to do these. Okay, fantastic. We're going to go through and start using APIs to pull out this information instead. I don't like to use command line tools. If I can avoid it, I like to write my own. That way I can run them in memory. So we can use the sec item copy matching function to allow us to go through and just search the keychain. So we'll have up here a couple of key points in here as we go about doing our search. So this sec return data is a Boolean flag of whether or not, as it finds each entry in the keychain, do you want to automatically try and decrypt it? Well, I don't want to spawn a whole bunch of pop-ups as I try and look through these ACL lists, so false. This sec return ref aspect here is going to say, for each thing that you find, don't just give me the metadata, also give me a reference to that keychain item. So I want to be able to use that later on if I think I can decrypt this to then pull out just that keychain entry's password. So we're going to set that to true. We can say give us all the attributes, how many results we want to return, if you just want to return like the first match or all of them, and what kind of keychain entry is this in the first place. Is it the cert, is it a key, is it a password, all that sort of stuff. So as we start digging into this and start looking at all the different things that exist on macOS, I showed already kind of the high-level attributes that you'll get for a password, but if we look at keys and certs, we get a whole lot more information. So you can see, in this case, we're looking at the com.apple.kerberos KDC public key, or sorry, private key, where you can decrypt with this key. Yes, you can use it to unwrap information. It's permanent, so it's always going to stay in the keychain. All the sort of stuff that's kind of associated metadata about this key. Same with certificates that are stored in here. So I go ahead and pull this out as base 64, because who knows what people are storing in their certificates. But go ahead and pull all that out. Again, it's all just metadata, so nothing kind of wrong going on there. Now, once we find something that maybe I'm interested in, like the Slack safe storage key, I go through and then I start looking at all the ACLs that are associated with it. So with that persistent keychain reference, you can go through and look at all the ACLs. You get the description, you get the list of trusted applications. This one is a little bit weird in that you can have a trusted application be a pointer to an application bundle, so in this case, applications Slack. It can be pointing to a very specific binary, so in this case, user libexec airport D, or it can be pointing to an application group. And so that's what we see down here, group : / airport. So that's an application group. That's a way that you can share keychain entries across various applications. There's also technically a keychain prompt selector that's supposed to identify, regardless of everything else, if you want to force prompt for a password to make sure that you get more explicit user consent. This is actually ignored. So it's still popped up in there. You still have to technically fetch it as you query this information, but that is just ignored whenever you go about looking for all this other information. So once you go through all that, you decide, yes, I want to try and export this thing. Two functions. This set keychain item copy content. This will actually get the encrypted data. This is specifically the function call that will either do a pop-up or get you the data. That will only work for general passwords and internet passwords. If you're looking for keys or certs, you have to use sec item export. And this is where you might run into additional errors as you try to export the first time. And it'll tell you, hey, you must supply a password as you export this thing. So again, not too bad, but so what? So we just kind of talked about looking at things. Let's do something with it. So I want to go through and export this data without causing a pop-up. Remember, that was my original goal. So as we go through and we look at this, if there is at least one trusted application for this entry that we're looking at, then in order to export without prompts, I need to make sure that that trusted application is associated with the right authorizations, so export clear, any, export wrapped, that sort of stuff. I need to make sure I match the partition ID. So if it's team ID something, I need to be in that team ID. If it's Apple : I need to be an Apple signed binary. And then my code signature that I'm running from needs to match that of one of the trusted apps or be a member of the Keychain access group. If all applications are trusted, this is a little bit of a misnomer. So even if you select trust all applications to access this thing, you still have to match the partition ID to be able to pull out that data without causing a pop-up. So only if there is no partition ID set, then does it truly become all applications can access this. So as we go through and we look at this, if there is an application listed, you pretty much need to be getting execution within that application. So think dilib insert libraries, dilib hijacking, can you just inject into it, like all these sorts of things. But I mentioned that something will be pretty interesting about that Apple : partition ID. Well, how can you get execution under an Apple signed binary? Execution within that context. Well, OSA script. Lovely. So OSA script, an Apple platform binary, the whole point is that you're running arbitrary JavaScript for automation or Apple script code. So you can run OSA script and some code, and anything that is trust all applications with a partition ID of Apple : now you are valid, and you can pull out that data without causing a pop-up. So pretty interesting. This technically also works for Python, because Python is an Apple signed binary. But as we've seen already, it's not going to be installed by default on most systems, so I fall back to JXA. And that's why the locksmith light JXA file is included as part of that project, so you can go ahead and pull that out. So now I want to talk about 3 kind of case studies, so using this to do something kind of interesting. So I wasn't expecting Microsoft to be here, so I have reported this, but I haven't heard back in 4 months. So I'm talking about it. So there are 2 additional attributes that are here that I didn't really talk about yet. So one is called invisible. So you can set an attribute on a keychain item that says, store this in here. Also, don't show it in the keychain access app. Don't show it to users, okay? There's also a general attribute that is just whatever you want to put in there, free-form text, store things. There's not a lot of applications that use this, but for whatever reason, Microsoft uses it a bunch. But the key thing to note here is this is metadata. This is not the thing that's encrypted, so anything you store in here, everybody can read. So I'm looking through the keychain, having a grand old time, and I notice something pretty interesting, Microsoft Office ticket cache. Well, that, from an offensive perspective, sounds amazing. Also, I noticed that the general attribute is this massive blob. So naturally, I take it out and I look at it. So it turns out to be a binary plist that has a set of all of your access tokens as they're refreshed. So you can see an example here. It's a whole bunch of nested keys, but it goes down to the time that your tokens expire and the specific tickets. So if you look down here, that EYJ is a common starter aspect for a JWT. So if we look at this, these are actually the JWT tickets for a whole lot of Microsoft services that you're logged into. So graph.microsoft.com, Outlook, Office 365, Teams, like all sorts of stuff. So naturally, I dig into this a little bit more, and I look at the scopes, like what can you do with these tokens? It's a lot of things. Things like files read-write all, mail read-write, OWA, access as user all, like all sorts of things. So yes, as a user, you get on the box, you can just pull down that keychain file or query in the API, pull this out, see all these, they give the expiration timestamps, you have all the tokens, you can then use them and hit the APIs. So great. I start thinking, well, if that's what's in just the general attribute, what on earth is being saved in here? Because that must be really juicy. I start looking into the ACLs that are in here. So the trusted application being Microsoft Outlook has a requirement string. It's valid. They're the only ones that can do export, decrypt, all this sort of stuff. There's the allowed key signature. So the partition ID says, you must be in the team ID Microsoft. All right, they did this right. What's in here? Nothing. So it took me a long time to figure that out because I thought I was just doing it wrong every time, and I couldn't actually get the data that's in there. For whatever reason, all of the stuff that I think they meant to put in the keychain is in the general attribute. So none of it's actually encrypted or protected in any way. So you can go ahead and pull all that and start playing around with all those API tokens. So another one I wanted to look at is Slack. So maybe 2 years ago now, a couple colleagues and I did a blog post on using Slack tokens and cookies for access on Red Team. We presented that to Slack, and at the time they said, you know, sorry, there's nothing we can do. Once you're on a Mac computer, you're like outside of our security scope, so we're not going to do anything. So they left all of their unexpiring cookies just on the computer in plain text, because you're on the computer. So naturally, we blogged about that, and people have been using that, and you can kind of log in to Slack from anywhere using these persistent tokens. At some point in the last year or so, Slack silently decided that, okay, yeah, that's probably not a good idea. Let's store some data in the keychain, and then we can go ahead and encrypt our cookies that way. So that is good. But I'm going to skip some slides and show the demo instead about how we can still abuse this. So let's see. Here we go. So this is going through looking at the Slack safe storage keychain entry on macOS. And you can see here that it is locked down to Slack. So fantastic. Just to show that this is going to work, I'm going to authenticate and show you the password that's stored in here so that whenever we do dump it out, you can see that it's the same. So you can see the +1B up there. So if we start looking at it, we look at the keychain entry for Slack. We can see, yep, it is Slack safe storage. You know, it has all this sort of information associated in here. We look at the trusted applications. It is applications slack.app. It has this awesome requirement string. Fantastic. They're doing things in a great way. Those are the only one that can export this in clear text. I like it. Application signature says you must be Slack. Okay, they are doing everything really well. And, oh, that's kind of covering it. Let's see if I can get rid of that. Okay, well, the bottom thing kind of covered it, but it said that you can't print out the password because you are not Slack. I'm running this as just that locksmith application straight from Xcode. So I look at the code signature for application Slack. Sweet, they're doing everything great. Library validation, hardened runtime. We already saw that this is a fantastic protection measure. Signed by Apple. Man, they are doing everything right. So one thing to note about that requirement string is it just says that you must be Slack and your signature must go back to Apple. There's nothing about a version. So considering how lax Slack was about the stuff that I talked about previously, it's like, well, okay, let me just download an old version of Slack and see if I can do things that way. So I found Slack version 3.1.1, just mounted it as a volume. Go ahead and check the code signature for that version of Slack, so in the volumes. Aha, no code signature, not using the hardened runtime. But it is still signed, it goes back to Slack. So fantastic. This means that I can ride that access via dilate insert libraries, get access execution into that code, and pull out the keychain entry. There should be one thing that is making you a little suspicious so far. In the original keychain entry, it points out that the trusted application is /applications/slack.app. I'm running this from volumes slack.app. So that doesn't match up. However, as we go through and we run this, it doesn't actually matter because the path that you're running it from isn't what's checked. It's actually just the code signature. And so since the code signature is just checking that I am Slack and signed, we're good. This takes a second because you can see a little pop-up down there. I'm getting verified that everything is still A-OK. And we can see it's still technically thinking that it's only supposed to come from application Slack. There's nothing in there about a version number in that requirement string. So there we go down there at the bottom, sensitive secret +1B. You can just go ahead and pull out all that data because everything else still matches. So a couple of things that were happening here. That path that you're actually pulling stuff from and executing isn't being validated. It's just the requirement string that's going on in there. And these requirement strings aren't locking down to specific versions. So you can go ahead and use this for all sorts of applications, dilate hijacking, dilate insert libraries, what have you, get execution and pull out that data. So these are just slides talking about that. The last one I want to talk about is still a little bit of an enigma, but kind of weird. So this is looking at computer dollar and com.apple.kerberos.kdc on your Mac. So if you're not familiar, if you have a macOS computer joined to Active Directory, you then get a computer dollar account, so you can authenticate as that, access into Active Directory. Outside of that, every macOS computer has its own entire Kerberos realm, KRBTGT, it's called the LKDC, the Local Key Distribution Center. You have all of that on your Mac. If you're ever curious about how you on your Mac can do an SMB share to somebody else on their Mac and you can authenticate over, same with VNC, all this authentication from Apple to Apple is happening over Kerberos. So you're negotiating your local Kerberos realms, getting TGTs like we saw before, getting service tickets, and accessing things that way. So if we start looking at the computer dollar account entry that gets added into the keychain, it's in the system keychain, fantastic. Although it has technically locked down to UID 0, but it says that if you're UID 0, your authorizations are any, which is a little weird. It's not locked down to any specific application that's trying to do things in the keychain. And there's also a weird thing where specifically for some of these older entries, you'll get errors trying to print out the ACL entries themselves. The error is saying that the contents are not simplified. Couldn't find anything anywhere as to what that actually means or how to convert it into a non-simplified version. But as we go through, with a standard user, you can't print out the plain text password, as you might expect. However, as root, you can get this without prompting. So because you do fall into that UID 0, you are the owner, you can do this. So it's a little weird. I wouldn't expect that just root, as we've already seen before, root is kind of locked away from doing a lot of admin-y things on macOS. This should be one of the things that's kind of protected that way. But the other thing that's kind of weird is if you look at this in Keychain Access, and you look at the access control that's technically associated with it, so while I can't pull it out, Keychain Access can, it says all applications are allowed to view this data. Well, that's kind of weird. Similarly, even though this says all applications, if you then click down to confirm access and then click back up and then hit save, everything kind of changes. And now we can actually see this data. We can see that all applications are trusted for anything. There's no partition ID. And so now even your standard user can go ahead and pull out this data without causing pop-ups. So despite this data still being kind of set in here, now anybody can pull it out. The same sort of thing happens with your com.apple.kerberos.kdc. So this means that as root, you can go through and pull out the private key, public key, and certificate for the local Kerberos on every Mac without causing any sort of pop-up. Now what that means, what I like offensively, but it kind of sucks defensively, is that if you have, like we see in a lot of places, non-Active Directory joined machines, and you go through and you pull out the private key, public key, and certificate, you can forge TGTs and service tickets back to that computer. So raise of hands, how many defenders, after a Mac compromise, rotate their local Kerberos certificates? Yeah, that's what I thought. So even if your user password changes, if you own the entire KDC, just like we see in Active Directory, you can just make tickets back, because that's all that's happening behind the scenes for this. So assuming that these services are turned on, that would give you access to file sharing, VNC, remote desktop, like all sorts of stuff. So definitely something to kind of keep an eye out for. And that's kind of the last of my talk. So I'll go ahead and open it up for questions. You could use the password that's in there to then encrypt other things. So just like you could, generate your own key and then do the same sort of thing. Yeah. Any other questions? Awesome. Thank you.